Hi everyone, here's your lesson on positive and negative integers in binary. This is going to be quite a small lesson, and it's actually just going to cover these two first points in the arrangements under computer systems. So by the end you should be able to describe and exemplify the use of binary to represent positive and negative integers using 2's complement, including the range of numbers that can be represented using a fixed number of bits. You should also be able to convert 2's complement numbers from binary to denary, that's just decimal numbers, our normal counting, and vice versa. Okay. Some of this will just be a recap from National 5, and there's just a little bit of new learning that is going into this as well. Okay, so we recap from National 5, going from a denary number or a decimal number to a binary number. So our kind of usual headings that we would do. Okay, so if we were using 8 bits, this is the 8 bits that we would use, or the 8 values we would use, starting from the right hand side for 1, moving to 2, 4, 8, and doubling it each time. If I had a number like, say, 150, and I wanted to convert this 150 into binary, I would start off at the 128, and I would take any of these values that I required and put a 1 underneath it. If I don't require that particular value, I put a 0. Okay, so starting off with 128, I do need that. So if I take off 128, I'm left with 22 still needing to get. So I don't need 64, I don't need 32, I do need 16. So if we take off 16, that leaves us with 6 to still get. So I don't need 8, I do need 4, I do need 2, and that makes up our 6, and I don't need 0. So this gives me 150. Just very quickly again, let's try another one. Let's go for 99 this time. So for 99, I don't need 128, but I do need 64. I do need 32. That will give me 96. So I just need 3, and I can get that from the 2 and the 1. So don't need 16, don't need 8, don't need 4, don't need 2. Oh, sorry, I do need 2. And I do need 1. Okay, so that gives me my 99. So 64 plus 32 plus 2 plus 1 equals 99. All of the zeros are ignored. Okay, so that's a little recap. If you were going that way, if we started off with a number, so if we started off with, say, a binary number and wanted to take it back, we could maybe do something like 0, 0, 1, 1, 0, 0, 1, 1. And we use the same principles. We ignore the 128 and the 64, but then we say 32 plus 16. Okay, the two numbers that we have here, plus 2 plus 1. Okay, and if you add all those up, we're going to get 48, 50, 51. Okay, so hopefully we can remember that from National 5. Okay, so range of numbers just basically means what is the smallest number and what is the highest number, and everything in between is the range of positive numbers that you can have. So just a quick example of this would be if we are using 8 bits. It's going to be similar to the one that we had before. So we're always used to using 8 bits, so that's the reason why I'm starting off with this. So if I said, right, what's the smallest number that we can make using 8 bits? A lot of people say 1, but it's actually changing all of these to 0. So the smallest number that we can make using 8 bits is 0. What's the largest number? Well, if we've got the smallest number by making them all 0, we would get the largest number by making them all 1. And if we add all of those numbers, 128 plus 64 all the way down to the 1, then we get 255. So we would say that the range for 8 bits is from 0 to 255. If we used only 4 bits, so let's get rid of some of this. Okay, we're going to do 4 bits this time. Okay, so 4 bits, 1, 2, 3, oh, I've added an extra one. Okay, so this is our 4 bits. Again, if we wanted to know the smallest number, we just make all of these values 0. So the smallest number is 0. The largest number is 1 plus 2 plus 4 plus 8, which is 15. So we would say that the range for 4 bits is equal to 0 to 15. We can make any number between 0 and 15. Try it with lots of different numbers. Try it if it was larger than 8 bits. Try it if it was, say, 10 bits. If you were doing that, you would use these numbers here. So this is our normal 8 bits. If we added a 9th bit, we would have the number 256. If we added a 10th bit, we would have 512. The largest number you could represent is by adding up all of these. The smallest is going to be 0 again. So try that out, please. Okay, so from now on, we're going to be, when we're working with binary numbers, we're probably going to be using binary numbers in this form, in 2's complement. Now, this allows us to represent negative and positive numbers, and it's actually the way that a computer would save binary. In National 5, we learnt just positive numbers, always just having, just kind of disregarding the idea of negative numbers. But this is the way that a computer would actually store positive and negative numbers using the idea of 2's complement. Now, I'm just going to give you the technique of actually solving one of these problems. If we just start off with the usual way that we would. We end up with these numbers. But I want you to have a look at this. What we are going to do with 128 is give it a negative sign. So we're going to convert our numbers exactly the same way, but this the most significant number, is going to be a negative number. So say I wanted to represent the number negative 13. The only way I can get a negative is by making this value on, or I'm giving it a 1 value. None of the other values will allow me to make a negative number. Okay, they are all positive numbers, so I must have that negative 128. If I put in a 64, let's just do the calculation up here. If I have a negative 128 and I add 64, I end up with negative 64. And then if I add 32, I end up with a negative 30. So I'm getting closer to negative 13. And I'm going to add a 16. Which gives me negative 16. So what else do I need in order to make negative 13? I need to add a 2 and a 1. And then I make these 0, which give me negative 13. Let's try another one quickly. This time I'm going to represent negative 77. Again, the only way I can get this negative part is by putting a 1 in the negative 128. I don't need 64 because that would take me to negative 64, but I do need 32, I do need 16, I don't need 8, I don't need 4, I do need 2, I do need 1. And if you add up 128 plus 32 plus 16 plus 2 plus 1, you will get negative 77. Okay, so let's have a look at an example going the other way. If we had a number such as this here, if we had 1, 1, 1, 1, 0, 0, 0, 0, and we wanted to work that one out, again we would do the same sort of process. So negative 128 plus 64, it's going to give us negative 64, plus 32 is negative 32, plus 16 is negative 16. Okay, so negative 16 for this particular number. If we were to say 0, 0, 0, 1, 1, 1, 0, 1, this would give us no negative number. Okay, so the negative 128 is not being used this time. So instead, we've got 16 plus 8 plus 4, okay, which is going to give us 24, 28, plus the 1, okay, which is going to give us 29. So note that this is not a negative number, this is a positive number. So using 2's complement allows us to store positive numbers as well as negative numbers. It just means that basically these are the numbers that you kind of play with. And this part here, which we would call the most significant bit, this part basically decides whether it's a negative number or a positive number. Okay. If we have a 1 at this side, then it means that this number is going to be negative. If you have a 0, then it means the number is going to be positive. So bear that in mind. If you are ever given a 2's complement number in binary, the most left-hand number, whether it's a 1 or 0, if it's a 1, then it means it's going to be a negative number. If it's a 0, it means it's going to be a positive number. So this takes us on to our kind of last part of this particular topic. Range of 2's complement numbers. Now we know how to work out the range of positive numbers. We just make them all zeros and we get the smallest number that that particular amount of bits can make. And if we want to know the highest number or the largest number, then we make them all ones. When it comes to 2's complement numbers, slightly different. Let's get back our values that we use for this. Now, assuming we're using 8 bits again for 2's complement, if we were just whilst I'm on this topic, if we were using 5 bits, it just means that the 16 becomes negative. So this is the part that kind of decides whether it's positive or negative, and then these are the numbers that we add on. Okay, so we'll just keep going with this. We'll make it 8-bit 2's complement. Now remember, this is our negative 128, and the rest of the numbers add on to that. So, what is first of all, the smallest number that we can make? Well, it's going to be a negative number. So the smallest number we must make negative, smaller than 0. Okay, so negative 128. Now, do I want to add on 64 if I want to keep this the smallest number? No, I want to keep all of these positive numbers away if I'm trying to make the smallest number. So the smallest number I can make with 8-bit 2's complement is negative 128. Okay, so what's the largest number that I can make? Okay, so put a line under that and we'll see what is the largest number that I can make using these same values. Okay, so this time, do I want negative 128 if it's a large number? No, So I make that 0, which indicates that it's going to be a positive number. Then I add all of these together. All my positive numbers in order to make the highest number it can possibly be. So if I do all of that, that's going to give me a positive number of plus 127. Okay, so the range of 2's complement 8-bit numbers is equal to all the way from negative 128 to positive, positive 127.